Morning all. Slightly early, so I'm going to waffle for a couple of minutes before we get going on this. My name's Lawson. I'm a solution architect, I think, for Red Hat. In reality, I'm a software developer who does AI, just hiding out in Red Hat. I've been working in the industry for around about 35 years. I did a lot of work involving AI and massive data analytics with government space for a long, long time. In the last sort of 10 years or so, I've been working extensively with OpenShift, which is Red Hat's enterprise strength Kubernetes container system. What we're going to talk about today is basically the ways in which the container revolution, specifically some of the new technologies we've got on the Red Hat side, are actually ideally suited for AI and machine learning workloads. I come from a Hadoop background. If anybody in the room likes Hadoop, the lights are very bright, so I can't see you. So shout or wave. I can see one person. I'm going to try and give a demo as well. The network here is a bit not very good, so I apologize profusely in advance. Also, the cluster I'm running is actually in an Intel data center. Those lovely guys at Intel have given us some kit, and it's behind a firewall. So I do get a bit of a slow response when I'm talking to the cluster. When I talk to customers normally, I say, please don't think that OpenShift is slow. Please don't think that Intel chips are slow. If you want to blame anybody, blame Chinese intelligence, because they are always smashing that firewall. Still got 4 minutes to talk. A little bit of an overview of OpenShift itself. OpenShift is currently on version 4. Version 4 is based on Kubernetes. We did something very nice with the 4th version of OpenShift, in that we actually absorbed a company called CoreOS that had something called the operator framework. In English, what we now do with OpenShift is we ship OpenShift as a number of what we call cluster operators. Cluster operators are little objects that sit on top of Kubernetes and own an individual object type. So you can extend the object taxonomy of Kubernetes without having to actually change the Kubernetes core. What this means in real terms, what this means in English, is that when you can do an installation of OpenShift, when you can do an upgrade, it's basically zero downtime, because you're updating individual applications that make a big application in their combination. And this ties in a lot to the AI side, but we'll get onto that once we start the slides and once I start the presentation. I'm kind of hoping it won't be as hot today. I'd like this talk to be longer than 25 minutes, because this is the coolest room in the entire venue. But I will get dragged off the stage if I go over 25 minutes. Do I start now, or do we just waffle for a couple of minutes? Right, cool. So today's talk is going to be very, very quick. I've got around about 8 to 9 hours of information. I'm going to try and get across in 25 minutes, so I'm going to talk very, very quickly. My voice is gone because I was talking to lots of people yesterday, and I was drinking last night. So I apologize if I actually fade out. If I fall down, will someone come and give me some water, or even better, some beer, and I'll be fine. So we're going to talk about the next generation of artificial intelligence and machine learning workloads, but from the perspective of application development. So the Red Hat approach to AI and ML, we've come late to the party. Going to be honest on that. Red Hat is basically a provider of facilitation software. We provide software on which people can build things. You know, we've had RHEL, the best version of Linux, for a long time. We've had OpenShift for about 6, 7 years now. Our job is to produce basically massive boxes of technical Lego that people can use to build systems. But we are quite late to the party on the AI ML side. And that comes down a little bit to the mechanisms that you have to do for artificial intelligence and machine learning. It's all about big data. It's all about huge amounts of data and repetitive tasks. But the Red Hat approach to AI and ML can be summed up in 4 basic sort of clauses. The first one is hybrid cloud, and that's incredibly important. That's immensely important. And the point behind that is that OpenShift runs the same everywhere. If you install OpenShift on Azure, install it on AWS, install it on bare metal, if you're brave enough to install it on ARM, we'll try to squeeze it onto Raspberry Pi at some point. Any workload you deploy to OpenShift behaves identically. It's the same configuration as code. We've abstracted the underlying infrastructure and technology away from the orchestration that's actually done to orchestrate the applications. We're talking about open source efficiency. Now, Red Hat is a different kind of company. I've worked for a huge amount of companies, and I intend to die at Red Hat, hopefully not that soon. But Red Hat is a different type of company. We basically take open source software and we make it production strength. We provide basically a subscription which gives you support for using our enterprise strengthened version of that open source software. And there's a little clause I always talk about with customers. I call it the 4:30 in the morning stack trace. And it comes from an example. I was the first person to bring open source software into the government. And I brought a project called Lawson, everyone knows that's a search engine, into a government agency. And I built a user interface around it, made it nice so it looked like I'd done something. And then I delivered it. And then I went home, and at 4:30 in the morning, I had a phone call from the agency saying, there's a stack trace. And so I had to get out of bed, rack into the agency itself, look at the source code, and it was all in the open source bit, which I hadn't written. And I had no clue what was going on within the open source software. But because I brought it in, it was mine. And I owned it, and I supported it. Red Hat provide a breaker. They provide kind of a safety net for that 4:30 in the morning stack trace. We provide you with the open source products, we provide you with the enterprise strength, and you can raise support requests on anything that we actually provide you with. The third one is intelligent platforms. What we're going towards, what we're moving towards with the Red Hat product set, is trying to be slightly more opinionated on the way in which our products work. Because in the old days, we used to produce a massive box of technical Lego and say, here's the technical Lego, build a car. And it's like no instructions on how to build a car, but here's a wheel, here's a piston for the engine. We're coming up with more opinionated approaches now. And one of the things I'll mention later is Open Data Hub, which is an open source set of data scientist tools that we can now bring down as a single operator and execute within OpenShift. And finally, intelligent apps. Is letting customers build intelligent apps using Red Hat products. This is very important to me because I was a developer for 35 years. I was a developer back in the days, before most people here were born, when you had to do everything yourself. And I came up against what I call the 70-30 problem. And the 70-30 problem was, I was getting paid a reasonable amount of money to be a contractor with the government writing software. And I spent 70% of my time not writing software. I spent 70% of my time building machines. I spent 70% of my time downloading frameworks, installing frameworks, configuring the tools I needed to write the software. So I was only spending 30% of my time writing software. And that's hideously inefficient. And what we're trying to move towards, especially on the Red Hat side, is to provide tools and technologies that up that to 95% of your time being able to write the code. But why containers for artificial intelligence and machine learning workloads? Well, the whole point with containers is that decoupling of application and infrastructure. I actually call it taint. And the reason I call it taint is the ops used to hate me. Because I used to rack up with a piece of software and say, here's the software you're meant to use. You'll need to install this version of the JVM. You need to install this database. You need to set this configuration. You'll need to, at 2:30 in the morning, you have to come in and tweak this environment variable. And all those things were taint that would actually taint the underlying operating system. So ops would install my machine or my application, and they wouldn't be able to put anything else on that box because it was tied to my JVM. It was tied to my framework. It was tied to my version of the database. The beautiful thing about containers is you abstract all that taint into the container, and the underlying infrastructure just executes the container. So if you're using a Java application, the JVM travels with the container. If you're writing a database, the database code, the database configuration is within the container. It's not in the core operating system. Agility of application creation. It's so easy to write stuff in OpenShift. And that sounds mad, but literally when I do these demos to customers, I rack up, I install OpenShift, I create let's say a node application that's built from source, and I have a running node application in around about 35 seconds. And people often ask, oh, what have you done? What did you pre-rec? What did you do in advance? It's like nothing. It's so fast to be able to create these different environments, and that's one of the advantages of it. On-demand execution, I'll get into this later because this is the big thing I want to talk about today. We got the ability now within OpenShift and within Kubernetes to execute workloads only when they are required. And that's very important because if you're running containers on a standard Kubernetes system, they have to be active at all times to receive traffic. So when you actually call them, they are there to actually respond to it. We've got this new technology, which I'm going to describe and hopefully demo, which allows you to create applications and install applications that only exist for the duration of time they're being called. I'll turn it on its head. They're offline when they're not being used. They're not consuming any resource. So you can stand up thousands of these applications, not consume any CPU, not consume any memory. The minute they're called, they're installed, they're executed. When they finish executing, they wait for a timeout, then they go away. And you can get a lot more bang for your buck in terms of running these applications. And it lends itself to doing experimentation because you only have to have the components of your experiment running when you need to have them. And you can persist your experiment results and data and all that stuff outside of the actual applications. And it elegantly solves the 70-30 development problem. With the tools and techniques that come with OpenShift out of the box, you get all the things you need to be able to start coding like that. You don't have to set up your machine. You don't have to install the libraries. You don't have to install the JVM and all those kind of things. And it's not about scale. This is the key thing, the most important thing. It's about dynamic scale. So artificial intelligence, machine learning apps, they need to scale up massively, but they don't need to be scaled up all the time. When you're running a Hadoop cluster, that cluster is always up, and it's always there to be able to execute workloads. And when people aren't using it at the weekend, it's just sat there ticking. It's using CPU cycles, it's using electricity. It's not being consumed. In the past, this was impossible due to the nature of infrastructure storage and the tight binding of the applications to the machines. Using containers breaks that binding. You have the application in a container, which is a piece of currency you can move around between your platforms. And with containers, and specifically with Knative, this has radically changed. In order to understand how this works, you need to understand the container mindset, what you need to think about with containers when you're actually writing these applications. And I love this first statement. I always use it with customers. Containers are file systems with delusions of grandeur. They are literally just file systems, but they're executed in process spaces and they think they're operating systems. But in reality, a container is just built from an immutable image that is just a file system. And to take advantage of the actual design features of Kubernetes, applications and experiments need to follow certain design patterns. Kubernetes was designed to be stateless. It was designed to be able to fire up the applications, lose the applications, recreate the applications. In the old days, we used to write applications that used to sit on boxes and run for months, literally months. I expect most people here work with companies that have a box in the corner of the room that you're currently supporting using eBay China. And you know if that box dies, your application's gone forever. This point with the whole cloud native approach to Kubernetes is you write your applications like sausage machines. So they can be stood up, they can have all their dependency and their configuration injected, and then they can go away, and they can be replaced, they can be moved around. And it's that agility of the application control and creation. An application should be effectively stateless between runs. And that's what I'm talking about with the sausage machine approach. And it's not a limitation, because you can use things like data grid, which is based on an open source Infinispan, which is an in-memory data cache, a NoSQL cache, or persisted volume within OpenShift. What a persisted volume allows to do is to stand up a file system and express that file system into the back of the container, but it's actually external to the container. So the container sees it as a file system it can write into, but you can actually destroy the container and recreate it somewhere else and reattach it to the persisted volume, and it can carry on from where it was. And that's brilliant because it introduces that kind of post-state, the state that actually survives between executions of the containers. So introducing Knative, I get very excited about Knative, and I haven't been mic'd, so they made sure that I stand in one place, because I normally walk up and down and wave my arms, and then I go to the toilet and forget I'm still mic'd. Knative as a concept is simple. It allows a container to scale down to 0 replicas whilst inactive, and then recreate when it's called. When you install an application in Kubernetes or OpenShift, normally you use a deployment. That deployment specifies the number of active replicas you have to have. So by default, you'll install a single replica. That application will be running at all times. If you install it using the Knative technology, it actually creates an ingress controller at the front, and it creates a mechanism that allows you to offline it to 0 replicas. Now, if you actually had an application in standard Kubernetes or OpenShift and you reduced it to 0 replicas, when you send traffic into it, you get a failure. You get a 500. The actual internal proxy and the internal router would not be able to push traffic to it. With Knative serverless, that is treated as an event to spin up the application. And there are 2 types of Knative applications that are supported within Kubernetes. The first is serving, and that actually creates an input point, an ingress point on the service. And that means that when you push traffic into it, it spins it up and responds to it. The second one is more important, and I think much more relevant to AI and machine learning, and it's called eventing. And what eventing allows you to do is to create a broker that lives within OpenShift, that lives within the namespace itself, that processes a new type of abstract event called a cloud event. And I love cloud events because they're incredibly simple. They've got a type and they've got a payload. And what happens is when you push one of these cloud events into the broker will look at the cloud event type, and it will look for triggers within the system. And if any of the Knative serverless are waiting on that trigger of that type, it will pass the event down to it. The arrival of that event into the actual application will spin the app up, run the processing, and do all those kind of things. The lovely thing about this is those brokers are by nature, by default, they're ephemeral. So they live within the actual namespaces, and if you lose the machine, bring it back up, all the state is gone. But you can back these brokers with Kafka. So you can set up Kafka to have a topic. That topic can deliver cloud events of certain types to the broker. And what that allows you to do is basically have a broker that's generating these events to drive the Knative serverless, but then you can temporarily replay the actual messages by just pushing the buffer back within the Kafka. And that allows you to replay experiments, to actually access experimental data being pushed into the Knative serverless via Kafka, and then just reset the actual temporal point to rerun that experiment. But why is this relevant to AI and ML? So AI and ML workloads are all about size and repetition. They're all about huge data processing, and they're all about doing things over and over again to get the results, to generate certain types of result. And most organizations are limited in this resource, either by size or cost. You know, it's very expensive to run up an AWS cluster. It's very expensive to maintain a Hadoop cluster. Containers and Knative technologies allow for massive experiments in much smaller footprints. It's all down to efficiency. You know, if you've got, for example, an experiment that's got 10 phases it has to run, 10 individual components have to be executed, there is no reason why those 10 components have to be resident at once. They can be resident in a chain, driven by Knative serverless, much smaller resource footprint. So you can do many more experiments on much less hardware. And OpenShift Kubernetes have facilities for targeted orchestration. And this is where it gets really sweet. How Kubernetes works is it has a number of, I'll tell a little joke, so I assume there's no Red Hat salespeople in the room. It has a number of worker nodes. And these worker nodes are basically buckets where workloads can be executed. So I used to describe to customers what you do is you stand up all these individual buckets within your Kubernetes system, and then you run your workloads over it. And I was taken aside by one of the chief salespeople at Red Hat. He said, you can't use the word bucket. It's too technical a term for salespeople. And it was like, right, okay. That just struck me as being amazing. But anyway, what OpenShift allows you to do is to do specific workload targeting on these buckets. So if you've got, for example, 5 worker nodes in your system, and one of your worker nodes has a huge amount of memory and some GPUs, you can actually have OpenShift orchestrate those workloads that require GPU to only land on that box. And one of the new features we've got of OpenShift in the latest releases is we've got the abilities of the boxes themselves to export the actual hardware requirements they have. So if you've got a box that's got NUMA zones, or you've got a box that's got GPUs, it can express through the OpenShift system that it has these kind of things. And then your orchestration, if you get a workload that says, I must run in this NUMA zone against this CPU, I must have access to this amount of memory, I must run on a GPU, OpenShift can automatically orchestrate that to the appropriate box. And that's incredibly powerful. It means you don't have to have a box or a cluster that has identical boxes. So I work with some banks, and what the banks do is they tend to buy a very expensive box for all their top-of-the-range services. And they go and buy the worst possible boxes they can for their developers off the back of a lorry. And they stand those up as worker nodes and label them as developer, and then stand up the prime node and label it as for the best. And OpenShift allows that kind of orchestration. It uses affinity and anti-affinity to make sure the workloads land in the appropriate places. And I say it's much more efficient use of resources means better results for less outlay. So we can talk about a thought experiment now, and this is where I get a bit more excited. Because I've been working with neural nets for a number of years, and I love the concept of neural nets, but I've never been able to build one properly. Because I'm... Any Java programmers in the audience? Any Go programmers in the audience before I start to insult Go? So I'm a Java programmer, and I've been a Java programmer for 25 years, and Go makes my teeth hurt. I don't know why. So I find it very hard to write experiments in Go. Anyway, long story short, what I've been working on is this concept called K-neural. And what it does, it allows to create neural nets using neurons, but the neurons are Knative services that only exist for the duration they're being called. The neuron itself uses Red Hat Data Grid, which is an in-memory data grid, to actually store the state of the neurons. So when a neuron is called via a cloud event, it spins up. The first thing it does is it talks to the data grid and it pulls off its memory state. It looks at the memory state, it looks at the thresholds, it looks at what it has to generate. If it exceeds a threshold in the way that a neuron normally exceeds a threshold, it will throw a cloud event back to the broker. And that cloud event will drive other neurons. And when the neuron has finished its work, it's offloaded. So you can build these hugely complicated systems with very small atomic components. And that's incredible. I mean, I've had some problem writing it because, I have a day job. So they won't let me do this all the time. I have to come to these events and sell software and things. But I've been working on this a lot. I've actually got the GitHub repo if I want to play with it. But I say neurons are perfect for this kind of system because they're atomic and simple. You provide the state when the neuron is created. You persist the state when the neuron changes the state. And when the neuron goes away, the state is still persisted. And if you keep your neurons simple, if you keep the actual state of the engine simple, if you keep the thresholding simple, it's a very, very nice way of doing it and incredibly fast. And I use the InfiniSpan Red Hat data grid for the memory. So it's an in-memory data grid that allows you to store NoSQL objects. So if getting slightly technical, what I do is that each neuron has a unique ID assigned to it. A unique ID is used as a key into the grid to pull the data off. And I say each neuron is represented by a tiny container, because you can build containers with very, very small footprints. We've got a technology we ship as part of OpenShift called the UBI, the Universal Base Image, which provides RHEL in a much smaller footprint. So you can build applications on top of a RHEL system, but the actual container footprint is very, very small. So these neurons are tiny containers. And I'm currently testing whether I can get 1,000, 5,000, 10,000, 100,000 of these things up and running at once. So demo time. So I'm aware I'm running a little short of time, so I'm going to show you a quick demo. And again, this is on the Intel kit, so if it runs slowly, please blame Chinese intelligence. I used to say blame Russian intelligence, but that's no longer allowed. So what we're looking at here when it starts up is basically, this is the standard OpenShift user interface. We've actually provided two user interfaces. One is for the administrators, and that's not actually true because it's for basically it's an object level dive into every object that you as a user can actually change. So I'll show you very quickly while this is rendering. If I go to the administration user interface, what it is basically it allows you to drill down into any component of the system. So I can drill down into all the deployments, drill down into all the services, the routes, everything I have access to I can drill down into. One of the lovely things, I'll take 30 seconds on this because this is really sweet, is part of OpenShift is we've now expressed the infrastructure on which OpenShift runs as objects within Kubernetes. So you can treat them as other objects. So you can change these objects in real time. So you can change the number of nodes you've got. You can change all these kind of really cool things without having to go down into the dirt and rebuild the system and do all that kind of stuff. The developer user interface is an opinionated user interface that we produce specifically to make developers' lives easy. Going to be honest about this, Kubernetes is hard. And people don't tell you that. People say Kubernetes is simple, go get Kubernetes, all this kind of stuff. I love Kubernetes. Kubernetes is one of the most elegant pieces of software I've ever seen. But it is painfully complicated. And it uses this model which they call eventually consistent, but everyone who actually uses it call eventually inconsistent. In that you actually talk to the Kubernetes control plane, change the object state, and then Kubernetes says, yep, done. And in the back, it goes away and actually does the physicalization of that. So you have that wonderful thing about being eventually consistent. But anyway, so what we're looking at here is an application I've written. So this is the K-neural stuff I'm actually running. I've got the data grid active. I've got something called Grid Connect, which is basically my way of actually interacting to the grid itself. The reason for that is I wanted to keep the neurons very small. So rather than having the connectivity information within the neurons themselves, the neurons just send very small packets to the Grid Connect, which does the actual physical connection and physical update of the data within the grid. Again, I'm just trying to optimize those things. A more optimized container, a much smaller container, is much faster to run, much faster to deploy, much faster to move. Over here, which is the cool bit, I'll make it slightly larger so people can see it, is I've got a Quarkus function. So Quarkus is a new version of Java. We basically made Java relevant again. Because I was a Java programmer for 25 years and I love Java, and Java got this terrible reputation of being slow. So we came up with Quarkus, and what Quarkus does is it pre-compiles all the class files. It makes the startup time of a Java application go from seconds to microseconds to nanoseconds, beautifully fast. So what I've got here is a single Quarkus application that's waiting for an event to arrive within the broker. So this broker here is actually got two triggers. One trigger is waiting for a Quarkus event, and I've got a subscription for that trigger for this Knative service. The other one is actually a tech talk event, and on the end of that, I've got a technology called CamelK. So CamelK is based on Apache Camel. It's an integration technology which allows you to write some very, very cool, very fast technology in very small amounts of code. What that does, it's very, very simple. It just pulls the image, it pulls the actual event off, and it just logs the fact it's got an image, an event. And I've also written, and I apologize profusely, I haven't changed style sheets since 1999. I find style sheets very hard to write, so this looks like an old school web app. What this does is allow me to actually emit the events themselves. So what I'm doing is I'm actually going to push an event, a Quarkus event, with a payload that has just a single key payload and Hello AI Summit in it. And I'm going to push that into the broker. So this is just basically throwing that into the system. And the broker I'm targeting, you'll see over here, is the K-neural broker in the actual K-neural namespace. So you can individually target these brokers based on the namespace themselves, which allows you to fragment the event model. So I'm going to emit that event. And if I'm quick, this makes it easy because the network isn't very good, you'll see that the application immediately fired up. But you'll also see that this one fires up. And the reason this one fires up is that this one actually emits an event of Tech Talk event. So when that event arrived within the broker saw that it was a Quarkus event. It pushed it down the Quarkus event trigger. The Quarkus event trigger actually spun up that Quarkus function. You saw how fast it actually spun up. The Quarkus event processed that and then re-emitted a Tech Talk event back to the broker, which kicked off the Camel K. It's a pithy example, and it's the best I can do with this network. But if you think about it, what you can do with your systems is you can break your systems down into atomic components, break it down into atomic microservices, write each one of those microservices as being driven by a cloud event and install it as a Knative serverless workload. And then you can write extremely complex systems, but not consume a huge amount of resource. And this is huge. When I talk to customers about this, this is what I wanted 20 years ago. And whenever I talk to customers about it, I'd like the customer to say, well, why don't you quit Red Hat and come work for us and write this for us? Because then I get to write software again. But then I remember how horrible it is to write software for a living. This is the next generation. The beautiful thing about it is when you use OpenShift, this comes out of the box. It's not additional configuration. You just install basically the operator to install Knative serverless, and away you go. So this thing is now flashing numbers at me. I think I've gone beyond. So that was basically the demo. We've got a stand over there. My voice is probably going to last for another 2 hours if people want to come and chat. I think the pub opens around about 11, which will make my voice work even better. But I'll say thank you for that.
Yes.
Questions?
Questions, yeah.
5 questions?
Yeah, 5 minutes.
Yeah, cool.
So we have 5 minutes for questions still, as we started slightly early. So if you have any questions, now's the moment. Oh, what the hell happened there?
There's a rush for the exit.
Question? Yes, there's one coming around to you.
Yeah. 1, 2, 1, 2. Yeah. All right. Thank you for the presentation. If I understand correctly, first quick question: do you really atomize the neural network at the level of neurons?
Yeah.
All right. So we are AI engineers, software engineers, and most of the time we need to create our own big deep learning networks, different architectures, a lot of neurons. Isn't it really like counterproductive to run every one of each node? And isn't it like limitation as if you don't see like I don't need to atomize it. I want an input and an output basically, right? So if I would have to do hundreds of thousands of nodes, does it really still help? To like
it does. What we do normally is we localize the networks for the. So if you're running, let's say, a huge amount of pods within a single cluster, we use the internalized SDN. And what we can do is actually have placement. So if you want to have a number of applications that are very chatty across the network, you can make sure they land on the same nodes or nodes that are actually close. But we've got a new technology called Submariner. Have you heard of Submariner? So what Submariner allows you to do is to put an overlay network over multiple clusters. So you can actually treat, what this overlay network does is it provides basically an overlay network over the SDNs of multiple clusters. So you can actually spread your workload out. But in answering your question, you can localize these things. So I've had a lot of customers who've got very, very sort of intensive application spaces, and they need to be close to each other to cut down the latency from the call from point to point. And what they've done is basically actually stood up a number of the worker nodes within OpenShift with black fiber between them, or basically in the same room, to get around that. So you can architect. The beautiful thing about the OpenShift side is that we're not opinionated in the way you actually install it. This is what I was talking about the box of technical Lego. If you've got a system that has to be massively network efficient, you can design those appropriately. I've got some customers and all they've got is 2 nodes. And these nodes are massive, sort of dual socket 96 core systems. And they do everything. I actually had one. I won't say the name because it's under NDA, but what they did was they actually created a CSI driver that expressed a PV. So you basically have persisted volumes, which are the way in which you store things offline on disk. They wrote a CSI driver that actually used memory for persisted volumes. So they could mount a file system into the containers itself, but when they wrote to that file system, they were actually writing into memory, just to get the speed of actual processing and pushing the messages about. I'm not sure if that answered the question. I think I might have gone off one way.
I think we have time for one more question if we can keep it short, thanks.
And maybe to add to that question, so how scalable is OpenShift if you look at your neuron architecture? So how many neurons do you think OpenShift can serve?
I say we used to be limited by the Kubernetes node count. And there are 2 things you look at. It's the number of nodes you can actually support in terms of the response time of etcd, because the more nodes you have, the more kind of overhead you have on the etcd side. And then it's down to the number of pods you can run on each node. And we used to be limited by the Kubernetes count for the number of pods on a node. Off the top of my head, I think it was about 1,000 you could do on a thing. The beautiful thing about the scalability side is that you don't lose anything by having tons and tons of little nodes, because we've optimized the way in which etcd works. So if you want to scale out your system by having small nodes but thousands of them, you can do that. If you want to scale it out in a more kind of horizontal way by having just a number of huge nodes and then scaling up the applications themselves, you can do it that way. So it's a bad answer to a question, but there are so many ways you can do it. The problem we've always had with this is that we try not to be opinionated, because the minute you're opinionated, you're forcing someone to do it that way. The beautiful thing about the OpenShift is you can hang them together whatever way you like. Does that make sense?
Yeah, a little bit, yeah. But maybe I can ask a second question, because you also have Hadoop experience. So did you already compare the performance of your Hadoop experience with what you're experimenting right now?
Yeah. We cool?
Yeah, just if we can answer that briefly.
Can I go and get a drink now?
Yeah, I think we can.
Cheers, thank you.
Well, thank you for that.